Alright, this is Mr. Gillum, and today we're going to learn about arcs and chords. So we got a few theorems today, which means we're probably going to have a few proofs on the homework. It says, the first theorem that we're going to talk about, it says in the same circle or incongruent circle, two minor arcs are congruent if and only if their corresponding chords are congruent. So what that means is this. It says, be the interpreter here, if this segment is congruent to this segment, no matter what, the arc length will also be congruent. But so if this is congruent to this, the arc length will be congruent to the arc length. Okay. And so if I wanted to illustrate another one here, if I said that this guy right here, this chord, was congruent to that chord, then I would know this arc length from there to there is the same as that arc length. If they were all three equal, this guy is equal to this guy, and this guy, they're all equal to each other. So if you have a chord, meaning a segment that touches the circle and ends on the circle in two places, and it's equal to any other chord, then the arc length outside that chord is congruent to any other arc length outside any of those other chords. Okay, so we have a little proof here, and I left the columns blank in the proof. It says we have a circle, and it says that arc QR and arc ST are congruent. We're trying to prove that QR is congruent to ST. Now, we just learned a theorem that says that basically, except for it says it backwards. So what we're going to do is this. We're going to use what we know about congruent triangles. We're going to have a little triangle proof in here. We'll write down the given, and what it tells us is that angle QPR is congruent to SPT, because I know that if the arc length is congruent, so is the central angle. We know that those are congruent as well. Okay, so if the arcs are congruent, their corresponding central angles are congruent. So that'd be a good thing to write down and highlight, because that's going to be one of the main things we use in our proofs. All right, we already know that QR is congruent to ST. Sorry, take that back. It is given, but it's not actually in the given. What we do know is that a radius is the same as long as it's from the center point on. PS is congruent to PT, which is also congruent to PR, is also congruent to PQ. Okay, any radius from the center of the circle, no matter where the radius is, it's equal to any other radii of the circle. So I'm going to write down that PR and PQ and PS and PT are all congruent. All right. Now that's enough information right there to prove that these triangles are congruent through side, angle, side. Side, angle, side. Okay, so we have a side, angle, side relationship here. So I know that these triangles are congruent using side, angle, side. And so at the end of the day, what I'm trying to prove is that QR is congruent to ST. If this is my congruent statement, I see that QR and ST must be congruent, so corresponding parts of congruent triangles are congruent. Okay, so one more time. As I'm thinking about my proof here, I'm thinking, okay, they tell me the arc lengths are equal. That tells me the central angles are equal. I said that all of these are radii. They all must be equal. I now have a side, angle, side. And so if these triangles are congruent through side, angle, side, then corresponding parts of congruent triangles are also congruent. Okay, so there's a proof there, a little example for you. And this is kind of just a real simple example to kind of reemphasize the theorem that we were just talking about. It says in the embroidery hoop, AB is congruent to CD, and that's already indicated here. And the measure of arc AB is 60. Find the measure of arc CD. Well, our theorem just basically said if the arcs are congruent, then the angle measures are congruent as well. So this is just a reiteration of what we just talked about. CD would also equal 60 degrees because the chords are congruent. Okay, so there you go, just a real simple example there. It says in the figure the two circles are congruent. It also says that the arc measure of MN is congruent to arc measure of PQ. So if that's the case, that tells me that this chord must also be the same. So if I'm trying to find PQ, this length here, I need to know what X is. So these chords are equal. I'm going to set them equal to one another. And then it's just an equation to solve. I know that X equals 8, but make sure we answer the question that it's actually asking us. It says find PQ. I know that PQ is 3x minus 7, and X is 8. I'm going to say 24 minus 7 is 17. So there's no like units or anything like that on it, so I'm just going to put 17 units as the length. Okay? So a lot of times the chords are congruent to one another. It's the important part to remember, especially if their arcs are congruent. Okay, we have a couple more theorems here. It says that if the diameter is perpendicular with a chord, then the arc length, I should say, it's bisecting. So that guy would be equal to that guy right there. And this arc length would be equal to this arc length. So if you have a diameter that is perpendicular to a chord, it is bisecting that chord and it is creating two congruent arc lengths. Okay? It also says if it is bisecting, and so if you see the information that is bisecting, that AB is guaranteed to be a diameter. Okay, so AB is guaranteed to be a diameter. All right, so on some of your circles today, it might not show the center and the chord running across. You might not be able to tell if it's the center or not. If it is bisecting the segment, it is a diameter. All right. Those are two more theorems we're going to learn about here, and we're going to apply that knowledge right now. It says in circle S, the measure of arc PQR equals 98. So all the way around is 98. And it says find the measure of arc PQ. So I'm just looking for this arc right here. All right. What I see is that this radius, or we could even make it a diameter if we want, is a 90-degree angle with this chord. That guarantees me that this part is congruent to this part, meaning also that this arc is congruent to this arc. Okay, so you're looking for that radius or that diameter. If it's making a perpendicular with that chord, you're guaranteed to have a bisection here, and the arc length will also be bisected. So if the whole thing is 98 degrees, I know that 98 divided by 2 would represent the arc length of PQ. 49 degrees. So we say the measure of PQ equals 49 degrees. And now, ooh, this is a fun one. Okay, we have a stained glass window here, and it says the diameter is 30. So all the way across is 30. Something I'm not going to write in there yet, but I'm going to keep in mind that's 30 all the way across. And the chord is 22 inches long. So the chord is 22 inches. Find JL. So this is the unknown length that I'm looking for here. Okay, so what I know is the diameter is 30. So I'm going to say that this radius is 15, and from here to here is also 15. I'm not going to write that one in there because my diagram is going to get a little too sloppy. It also says that this is 22 inches long all the way across. What I notice is my diameter is making a perpendicular with my chord. That guarantees me that this and this are congruent. Those two segments on either side of that chord are congruent, as well as these arc measures. I'm not going to write that in there for now either. But it says the whole thing's 22, so I know that one side of it would be just 11 inches. All right. Now again, and this is something that you just kind of start to get clever with as you do more and more of these problems. What I'm looking for is this unknown right here. And so right now the segment addition postulate will be something you might want to try, but I'm going to go ahead and do this instead. I'm going to make this a right triangle. Everything always leads back to triangles, it seems like. I know this side is 11, but it would be really nice to know this, because then Pythagoras says we can just use the Pythagorean theorem and find this unknown value. Luckily, this little triangle that I drew in here, this distance is a radius. So I know that if the radius is 15 here, the radius here is also 15 inches. And so now the problem becomes much easier now that I've drawn this auxiliary line, that line that wasn't there before, because I have a right triangle and I have a leg and a hypotenuse. I'm looking for the unknown. It's just a Pythagorean theorem problem. But if we didn't know that this was bisected, we wouldn't be able to do any of this, and that's really what the practice is for today. So let's go on and we'll go ahead and solve for the unknown. We're going to say that 11 squared plus the unknown squared equals 15 squared. And we'll solve it from there. And I've been getting in the habit of not showing my work here when I'm reducing these square roots, and I've noticed that some of us still don't know how to do it. If I'm factor treeing 104, I'm thinking 52 times 2, 26 times 2, 13 times 2. And this is one big multiplication problem. 13 times 2 times 2 times 2 would be 104. What I know is that 2 to 2 is 4. Okay, and it's under the square root, so I know the square root of 4 is 2. So that allows me to bring out a 2 outside of the square root sign. What I still have in here is a square root of 13 times the square root of 2, leaving me with a square root of 26. There's no perfect squares in that. So at the end of the day, my unknown is actually a distance of 2 root 26. Now, it is a quadratic equation, but because we're talking about a distance, I wouldn't need the positive and the negative version. I would just need 2 root 26. And so if I'm asked what JL is, I would say JL represents 2 root 26 inches, or it would probably be better to even find an estimation, because we don't measure things in roots. 2 times the square root of 26 is 10.2 approximately. Okay, this would be the exact answer. This would be the approximate answer. Okay. Finally, the last theorem we have here says that if the chords are congruent, they must be the same perpendicular distance away from the center of the circle. All right, so if we know that these guys are equal, the perpendicular distance must be the same from both of them. Okay, so if I drew another chord that looks about equal, its perpendicular distance would also be the same. All right, so and specifically this example, what it says is on your paper, it says Lx equals Ly only if FG and JH are congruent. Okay, so they must have the same perpendicular distance from the center if the chords are congruent. So looking at this one here, it looks like a confusing diagram, but it's really not that bad. It says that Wx is equal to xy. So you can see this chord is equal to this chord. That tells me that their perpendicular distance must be the same away from the center. It says to find AB. So what we need to do is we need to find that length. If I know that they must be the same perpendicular distance from the center, I can make an equation and solve the equation for my unknown value. Make sure that you don't just stop right there. That's great that you found what the unknown is, but we need to make sure we answer the question. So to define the length of AB, we know AB is represented by 5x, and we know the unknown is, in this case, 2. So I know that AB must equal 10, and this doesn't say what units or measurement we're using, so I'm just going to say 10 units. So we do understand that we're not talking about a degree, we're talking about a distance, a length. All right, that's really it for today. Hopefully you can apply these 3 theorems to your homework and be successful writing those proofs.